Hi everyone, my name is Neha Kadam and this is the fifth lecture on printed circuit board fundamentals. Table of contents. We will be covering in this lecture about star ground, analog and digital separation, ground planes, slotted ground planes. Now here, this is a star ground. The star ground philosophy builds on the theory that there is one single ground point in a circuit to which all voltages are referred, and this is known as the star ground point. As you can see in this example, it can be better understood that the multiple conductors extending radially. Here you can see in a blue these traces from the common schematic ground resemble a star. The important point here is that the star ground system is that all voltages are measured. Here you can see all these voltages are measured respect to a respect to a particular point in the ground network. However, this star ground philosophy may seem easy to understand, but it is difficult to implement it practically. When the power supplies are added in a circuit like this, they either add unwanted ground paths or their supply currents flowing in the existing ground paths are sufficiently so large or so noisy so as to corrupt the signal transmission. This particular problem can often be avoided by having separate power supplies and separate planes for the various circuit portions. Now moving on to the next slide. Slide talks about separate analog and digital grounds. So if you're working with the mixed signals, which has analog and digital circuit portion in it, then you have to keep in mind that the analog circuit should be separate from the digital circuit, which means that you should have a separate analog and digital supplies with separate analog and digital grounds, and that ground portion should be joined together at the star point, and that way you can use it in your PCB. And for this, I'll take an example of a digital circuit. Uh, if you are using TTL or CMOS, then they draws large fast current spikes from its supply during the switching time. As a result, signal may be noisy and this can interfere with the analog circuitry. While on the other hand, analog circuitry is also quite susceptible to noise on both power supply rails and grounds. So it is advisable to separate analog and digital circuitry on the PCB to prevent any digital noise from corrupting analog performance. Now moving on to the next slide. Now this slide talks about the concept of ground connection for an analog to digital converter. Here in this circuit you see this is a converter, and this AGND stands for analog ground and this DGND stands for digital ground. And these both grounds are tied together to a system analog ground. And here we see internal digital current flowing here and external digital current flowing through a low impedance analog ground. So this kind of arrangement you might have in your PCB design. Uh, let's see here. If the analog ground and digital ground pins are connected in this way, the digital noise immunity of the converter is diminished somewhat by the amount of common mode noise between the digital and analog grounds. So, however, since digital noise immunity is of the order of hundreds or maybe thousands of millivolts, this factor is unlikely to be important. The analog noise immunity is basically diminished only by the external digital currents of the converter itself, flowing in the analog ground. These current you see here, external digital current returns I'm talking about, these current should be kept quite small, and this can be minimized by ensuring that the converter output uh, don't see a heavy load. So for that, the good solution would be is to use a low input current buffer at the analog to digital converter output, such as CMOS buffer resistors IC can be used, and they also this type of buffer resistor also forms uh, filter RC filter, and which helps in producing a more refined signal at the output. Now here, if we see, if the logic supply to the converter is isolated with a small resistance, as you can see here R, and decoupled to the analog ground with a capacitor value of, let's say, zero point 0.1 microfarad, all the fast edge digital current of the converter will return to the ground through the capacitor and will not appear in the ground circuit. If the analog ground impedance is maintained low, as it should be for adequate analog performance, additional noise due to external digital ground current should rarely present a problem. So here, this kind of arrangement you can use when you are designing the circuit, and if you're working with the mixed signals. Now let's moving on to the next slide. Now, this slide talks about ground planes. To implement a ground plane, one side of the double-sided PCB or one layer of a multi-layer one is made of continuous copper and used as a ground plane. So the theory behind this is that the large amount of metal on the ground plane will provide low resistance, and because of the large flattened conductor pattern, the inductance will also be low. Such a ground plane offers best possible conduction in terms of minimizing any false ground difference voltages across the conducting plane. See, the importance of maintaining a low impedance on a large area ground plane is critical to all analog circuits today. The ground plane not only acts as a low impedance return path for a decoupling high frequency currents, but also it minimizes the electromagnetic interferences in the circuit. And I hope you remember in the last lecture we talked about the shielding action, how that can be provided to remove the electromagnetic interference. So that is also one of the one of the thing we can use to avoid electromagnetic interference. And the next point here talks about ground plane concept can also be extended to include voltage planes. A voltage plane offers advantages similar to a ground plane, that is a very low impedance conductor but is dedicated to one or more of the system supply voltages. So similar to your ground planes, if you're working with a multi-layer PCB, as you know, you can have multiple ground planes to work efficiently on your design. On your design. Uh, the same way, you can have multiple voltage planes, and that might fasten the flow of electricity in the in your circuit design. So thus the system can have more than one voltage plane as well as ground planes. Now the next slide is this digital currents flowing in the analog return path create error voltage. So here you see on the right side this circuit, the top one illustrates it is basically the illustration of a situation where the digital return current here is this is the digital circuit and this is the analog circuit, and this is the digital voltage, this is the analog voltage, and here you see ID stands for digital current and IA stands for analog current, and they are connected through a ground reference point here. Okay, So here this circuit illustrates a situation where the digital return current modulates the analog return current. The ground return wire inductance and resistance is shared between the analog and digital circuits, and this is what causes the interaction and resulting error. And also the voltage drop across this here will be some, but if we consider over here, there will be a lot of voltage drop here. So this is not a very good design. So instead of this design, we can use another design like this. And here you can see what change has been done. A separate path is provided here. So this is a possible solution to make the digital return current path flow directly to the ground reference. This is a fundamental concept of a star. As you can see, this is acting like a star ground, and different paths are connected from this ground potential. Implementing the true single point ground in a system which contains multiple high frequency return paths is actually difficult because the physical length of the individual return current wires will introduce parasitic resistance and inductance. So here parasitic is basically are the hidden resistance or hidden inductance or hidden capacitance in the circuit, which can make obtaining a low impedance high frequency ground difficulty. In practice, the current returns must consist of a large area ground planes for a low impedance to high frequency currents. With a low impedance ground plane, it is therefore almost impossible to avoid these shared impedances, especially at a high frequencies. So on the left, it says the same thing. In this case, the digital return current modulates the analog return current. This is talking about the top circuit. And a possible solution is to make the digital current path flow directly to the ground reference here. So this is a better design. Now moving on to the next slide. Now here it says, how do I prevent digital logic ground currents from contaminating my low-level analog circuitry? So if you're working in a mixed signal, so it might happen that your digital currents uh, digital logic ground currents can interfere with your analog circuitry, and they can basically make your circuit not work not in a proper manner. So for that, the one of the solution is that you can use a split. You can split the ground plane. Here you can see a slot is given. This is your PCB. This is your PCB, and let's say here a slot is basically given to avoid this kind of problem. And a VI is attached over here, and these are the return current paths. These are the return current paths. So you can slit the ground plane so that high current does not flow in the region of a precision circuitry, instead forcing it to flow around the slit. So this is our slit, and the current is flowing around the slit, and this can possibly solve the problem, even though the voltage gradient will increase at this point. And in these parts of the ground plane where the current does flow. In addition, ground plane slot will significantly increase the crosstalk between traces that cross over the slot, and the larger loops formed by the return current paths will radiate. So here the most important thing is to remember that if you are trying to create a slot in your PCB design, then there should be no traces crossing over the slot. If a trace does cross over the slot, then you need to ask yourself that where is the return path of for the current goes. So remember that return current follows the smallest loop area possible. So you have to keep this thing in mind. And also the ground planes solve many ground impedance problem, but not all. Even a continuous sheet of copper foil, if you use as a ground plane, then uh, it will have some residual resistance and inductance, and in some circumstances they can be enough to prevent proper circuit functioning. So as it is mentioned here, potential problems, especially in a large complicated systems, you cannot route a trace over the split in the plane. So this is the same thing, and it is always better to have only one single reference plane for a system instead of having a slot. Now moving on to the next slide, and in this slide we see two different designs, and they have a slot in between, and here also you have a slot in between. This is a slot. So here, if you do have a split in the ground plane and run traces across the split, like you see in this left figure, there will be no written path near the trace, and the current will have to flow in the big loop. So you might have a big loop in this type of circuit arrangement. So current flowing in big loops produces radiation and high ground inductance, and which is not good for your circuit. Whereas here we see, if you must split the ground planes and run traces across the split, you should do it as shown over here by connecting the planes together at one point, like a bridge, and routing all the traces so that they cross at this bridge point. So this is, here you see, is a bridge point, and all the traces are crossing here, and you will have provided a return path for the current directly underneath each of the traces. Hence here in this type of circuit arrangement, there might be a small loop area, and this is still a better design compared to that one. So here it says the same thing. There is no written path near the trace, and the current will have to flow in a big loop. Current flowing in big loop produces the radiation and ground inductance. And here, by connecting the planes together at one point, bridges, routing all the traces so that they cross at this bridge point. So this type of design provides a written path for the current directly underneath each of the traces. Now moving on to the next slides. Now this slides is basically the summary of what we have covered in this lecture. And it says partition your PCB with separate analog and digital sections. Do not split the ground plane. Use one solid ground plane under both analog and digital sections of the board. Route digital signals only in the digital section of the board. This applies to all the layers. Route analog signals only in the analog sections of the board, and this applies to all the layers. The key to a successful PCB layout is to use of routing discipline. So a PCB with a single ground plane and partition into analog and digital section, and following a discipline in routing, it can produce a good PCB design, and it can solve most of the difficult problems. And if the layout is done properly, the digital ground currents will remain in the digital section of the board and will not interfere with the analog signals. So the routing, however, may be checked carefully to ensure that the above mentioned routing restrictions uh, are basically followed. So the key to a successful PCB layout is that it should have a proper partitioning, and it should follow a routing discipline, not to split a ground plane. So this is it in this lecture. Thank you so much for watching this lecture.